ourselves of what isoquants are. So isoquants show all the combinations of inputs that can be used to produce some kind of constant amount of output. Can be used to produce some level of output. So different isoquants will represent different amounts of output, like 5 units of output or 100. And each individual isoquant is showing like all the different combinations of inputs of x1 and x2 that can be used to produce 5 units of output. Or separately, in a separate isoquant, the different combinations of x1 and x2 can produce 100 output. So remember, the higher isoquants represent higher output, making some assumptions about our production functions in general, and different technologies lead to different shapes of these isoquants. So the shape depends on technology, and we kind of saw a few different types of technology. So we saw kind of Cobb-Douglas production functions, which have these nice kind of smooth isoquants. We saw perfect complements in production, which have these right angles, these kind of Leontief, they're sometimes called, but these right angle isoquants. And we saw these straight line isoquants, and we have perfect substitutes in production. So that's what isoquants are, just as a reminder. So them a couple chapters ago. Now, what isocosts are, which are these new, so this is new. We've learned about isoquants before, but isocosts are new. So they show all the combinations of inputs that have some total cost or some cost C. Where different isocost lines will have will represent different total costs of production. And so how to think about isocost lines is here's the cost of producing, the price times the quantity of each of the inputs, and we're going to set that equal to some C. So C could be like 5 or 10, and that different levels of C are going to represent different isocost lines. So we could rearrange this to get like a function of x2 with respect to x1. And that's going to allow us to graphically think about how to represent these isocosts. So I'm going to move W1 and x1, I'm going to subtract it from both sides. Then I'm going to divide both sides by W2. Then I just have x2 over here. So that's what I'm doing here. So it's going to be C minus W1 x1, and we're dividing both sides by W2, so we have this. This is an equation for a line. So C is like the intercept of this line. If we're going to graph x1 on the x-axis and x2 on the y, this is going to be the intercept. You can think of this as y equals mx plus b, where like the slope is W1 over W2. In fact, it's negative W1 over W2, to be careful here. So different levels of C represent different total costs of production. So how we can kind of think about this minimization problem, I think I'm going to be able to fit it on the screen. think of this minimization problem that we just had on the last board. And I'm going to keep writing down here, then I think we can graphically represent what we're going to say over here. Problem as finding a point on an isoquant, so finding a point on some level of production that's on the lowest possible isocost curve. Slash line, whatever you want to call it. So we want to minimize the cost of producing Y units. So we take that isoquant that represents those Y units, and we want to get on the lowest possible isocost line that allows us to produce that level of output. And higher isocost lines represent higher costs, right? The higher C is, the higher the intercept. So we want to be on the lowest possible isocost line, because that represents the lowest possible cost. And we want to find the one that just touches the isoquant at that level of production we're interested in. So let's kind of represent what that might look like over here. And let's just give a nice easy case where we have this nice shape of these isoquants. So x1 and x2. Here's, let's say, an isoquant. Right, this represents some level of production, like Q equals, this is the level of production, maybe I should say Y to use some number. Let's say it's like 100 or something like that. So, different isoquants are going to have different levels of production. And that problem that we wrote out before is how do we produce this Y, it's 100 here, but think of it in a general sense, the lowest possible cost. What I'm saying is we have these different isocost lines that have different, the higher the cost, the farther they are from the origin. And so we might have one up here, and the intercept is C over W2, and that C is, fairly high. And the slope is negative W1 over W2, just like the slope we had here. This is like an isocost. And we can, with this level of cost, we could definitely produce 100 units of output here. But we can probably imagine that there's some lower isocost that represents some lower total cost where we can still produce this 100 output, or this level Y of output in general. Well, that's going to be, let's try to draw it a little bit better here. The isocost line, again, this is just going to be a different C, a lower C, but it still has the same slope, negative W1 over W2. If we have these nice, smooth isoquant lines, and we have this nice interior solution, then we're going to get to this point here, where there's a tangency between the isoquant and the isocost. And that's telling us the optimal level of inputs that minimize the cost of producing this many units of output. So this is I'm going to erase this board in a second. This is a nice, smooth isoquants that have these nice interior solutions. We don't have any kink in the isoquants that we saw sometimes with perfect complements in production. We don't have a straight line for our isoquant with perfect substitutes. So we have this nice kind of like easy case. We have this tangency condition, which is our optimal condition. Remember, that's very similar to the tangency condition that we kind of saw with consumer maximization problems as well. There is like a fundamental difference here, right? We're thinking about we want to be on, we're constrained by the technology of this isoquants. and we want to pick the lowest ISO cost line possible. That's a bit different than consumer theory. Because remember, we are constrained by our budget constraint there. We want to be on the highest indifference curve possible. So it's a little bit different, but you can see the similarities between these two types of problems.